Shalom. Ma shlomcha Tel Aviv. So today we're going to be talking about blockchain security. Even though the media are saying I have a blockchain security company, it's not true. It's just a side project I did last year. So how many of you have looked at smart contracts, doing smart contract development? 2, 3, 4, 5 people in the room. So it's a good thing because I'm going to explain what's a smart contract anyway. So what we're going to be discussing about today is basically what's a smart contract, the current limitation of the most popular platform for smart contracts, which is Ethereum. And we're going to look a bit deeper on the actual bytecode and the assembly used for like smart contracts and what to expect in the future. Because even though Ethereum is currently like the most popular platform for smart contracts, and keep in mind this is a project I worked on in February of last year, so almost 1 year ago. Back then, people were still not talking about ICOs and all like those things about smart contracts. So my personal opinion is currently like Ethereum, even though it's popular, is probably going to be replaced either like this year or next year by like a much more mature like virtual machine with a much better architecture to actually develop smart contracts. So last year a lot of things changed actually. Well, a year ago blockchain security was not a thing. No, it's actually an actual thing. And even media like quoting me saying that I'm the CEO of a blockchain security company, which I don't know how to take it. It's kind of funny, but it's a bit embarrassing. So one of the main things that happened last year is security tools have been released around like smart contracts and everything. And before that, there is not many security people who actually looked at everything related to blockchain, and especially for like many reverse engineers, it was something looked at, like web application or mobile application. It's cute, but it's not worth much attention. But it's changing, and you have like companies like JP Morgan. They did a fork of Ethereum called Quorum that are trying to like attract more security people to actually like review their code because they have an open source platform. A few weeks ago, Cisco Talos published a bunch of bugs that they have found, including some in the actual Ethereum virtual machine. Well, it was bound to happen sooner or later. And we're going to talk about like the actual risk of like smart contracts. So the good thing is if you have been reading the news over the past 6 months, you have heard like many ICOs have been hacked, and in some cases it was mainly because of like actual smart contract vulnerabilities. I'm also going to be discussing of what could potentially replace Ethereum in the future. And also, like a lot of like new languages appeared and emerged last year, or about to emerge, like Plutus or Simplicity, which is like the exact opposite of like current languages. So they're pretty trying to make it like easier and like more simplistic from like a language point of view. So let's start with the actual virtual machine and the actual compiler. So Solidity is the name of the compiler to compile smart contract for Ethereum. What it takes as an input, we're going to see it in later slides, but it takes like what looks like JavaScript code and translate it into like Ethereum bytecode. So like similar like to like most of like virtual machine that you would know, with an interpreter. And Porosity is the name of the tool that I worked on last year and which I'm going to present, which basically take like bytecode as input parameters and like decompile it, and you can also like run dynamic analysis on it. So, well, those are like pretty old slides, but currently like Ethereum is like quite popular. When I first like gave that presentation over the summer, Ethereum was popular, but we were still not sure if it was popular. Now it's like number 2 in terms of market cap as a cryptocurrency, and it's also like the number 1 platform we hear about when it comes to like people doing like ICOs, even like tokens. There's like some garbage stuff called like banana coin using like Ethereum smart contract. There is a lot of stuff like using smart contracts. Most of them are like mainly garbage, but they're still trading actual like dollar value on it. So if you're a criminal, it's an interesting target because it's low risk and high gain, because you don't need to like send the money to like some bank account or like to ask some like Swift service bureau. You don't need to have like remote SMB 0 day and to patch like the Oracle like database in memory. It's just like a piece of like pseudo JavaScript code that have been compiled, which is like available everywhere because it's transparent. You may not have the actual source code, but you can always like disassemble it or reverse it. And like the thing to keep in mind is like those smart contracts usually, they're gonna be like a few hundred lines of code. So if you're an attacker, it's actually a great target. And I would not be surprised that North Korea is like looking more to like targeting ICOs. It's already like targeting like cryptocurrency exchanges. Well, like those numbers like pretty low now. Some like report got published recently saying that last year like almost like $400 million got like stolen from ICOs and stuff. So it was definitely like a big target last year. It's going to be a bigger one this year. But instead of like targeting ICOs or investing in Ethereum, I wrote a decompiler, so my loss. So one of the actual interesting things that happened also in November, so it's a bug I'm going to describe later on, is some random dude was complaining that he accidentally froze, well actually it's like not even 150, it's like $450 million of like cryptocurrency because of some like dependency to a third party library, which I'm going to describe later on. So like it's still like very experimental, and the amount of money being lost with the actual technology is proving it. So it's one of the main reasons. Like I'm going to talk a bit about the actual limitation of the Ethereum virtual machine. You're going to see a lot of the actual design is kind of like limited, even like the ways they're dealing with registers. It's like a stack-based like registers. It's kind of like really ugly. And then you have like potential like alternative like coming up now, like Canada that have like proper like registers. They are building a more mature VM. So it's becoming interesting, at least from a research point of view. Because if you're a researcher, you don't really care if it's useful or not. You just like to look at stuff and see where it's broken or where you can actually break things. So here is basically an example of a smart contract. As you can see, it's like very simple code. It looks very similar to JavaScript. So here it's basically if you want to write like your own coin or your own token, well, that's all you need. You would need like those like at least 40 lines of code. And once you use the Solidity compiler from Ethereum, you get this actual bytecode out. And at the same time, it's also going to generate like the API interface, which is like the equivalent of like the PDB, if you're familiar with like Windows development application, except that instead of having like a 4 megabyte PDB, you're going to get like, that piece of like JSON code, which is going to describe all the function and their actual parameters. And each function is going to have a signature. So every time you call a function in a smart contract, you don't use its actual name, you use its actual signature. Memory management, that's where you kind of see that, it's still cool, especially since they were like the first main platform. That's also one of the things to keep in mind with Ethereum, because I don't want to bitch like too much about them. But they're basically like the first platform like to demonstrate a utility for smart contract. And basically, a smart contract is like a software layer on top of like blockchain. Until before that, like blockchain was purely used for like data, not to actually execute code. And with Ethereum, it changed. They added like that software layer. So obviously, since it's inside the blockchain, it means it's also immutable. And we all know like how painful and costly it could be to have a piece of code that you could never patch. I mean, I'm sure they had good intent, but you know, like it creates a lot of issues. So regarding the memory management, you have like 3 types of memory. So obviously, you're gonna have a stack to pass like parameters to functions. Here, you would use like the stack to pass parameters to functions, but also to the virtual machine instructions, because you don't have any like actual real registers. Everything is like stack-based, and it's limited to like 1,024 entries. So obviously, you have issues like stack underflow that happen a few times, and then you have 2 types of storage. So like a volatile memory for when you work with strings, and if you do like operations on them, or if you use like hash, like cryptographic hash functions. And then you're gonna have that permanent storage that you can easily recognize whenever you're disassembling a smart contract with the store and sload instructions. Which is kind of where it gets interesting, because well, that's where you have like the actual data that you want to keep. Basic blocks, so just like with like traditional like instructions or CPUs, you're gonna have like your jump instructions, and actually to find like a basic block, it's pretty easy, at least with smart contracts, because they have an additional instruction called jump dest, which is most of the time there, but not always, due to some compile optimization, because it does not do anything. It's just basically saying, okay, that's like the actual destination or the entry point of a new basic block. And then you have like all your jump instructions. So of course you have like conditional jumps. And where it kind of gets tricky, like I said, like the actual stack is like used for everything, even to pass like parameters to instructions. So you have like those weird instructions like swap, like to swap like entries in the stack. To duplicate, you have dup, and then you have like the pop push. Well, they kind of like mess with the stack a lot because they don't have registers. So basically, even when you want to do like a jump, it has to push like the destination first, like the destination address, and then you would have your jump. But in some cases, at the entry point of the function is going to push like the destination of the last basic block of the function, and then it's going to do a bunch of like random operation, and then like it's going to like do a pop to recover it, and then jump in it. So that's why you often need, even like in the case of the actual decompiler, or even like for static analysis, you kind of need to do like some sort of like dynamic analysis where you need to emulate most of the actual stack operations to keep track of the basic blocks. The Ethereum virtual machines has a bunch of instructions, so it's kind of like a rich VM, but not too rich. So you're gonna have like all those regular like operations, like for like arithmetic operations. You're also gonna have some like blockchain-specific instructions, like the environment and block information. So like on Windows, like you have like the process environment block that contains all the process parameters. Here you would have something similar regarding like your actual block. If you think of like your blockchain as an actual like current process, and then all your like stack and memory like operations. You have like some logging operations, although like very few like smart contracts use them. And then you have like some pre-compiled instruction like SHA-3. So let's have a look at what the actual like assembly look like. So here, say for instance, like here, that's how you would do like an actual addition. If you want to add like 2 plus 1, so you have like to push like 1 and 2 on the stack, and then you call the add instruction. So that's already like 3 instructions just for an add. So we're gonna use the following syntax, like the EVM pseudocode for like for this talk to make it easier to understand. Then you can also call third-party libraries. That's where it kind of gets interesting in some cases. And in the case of parity, when the guy throws those like $300 or $400 million, it was due to like a call instruction that was not like properly filtered. So like one of the actual parameters is like the address of a function. There are only like 4 addresses that are hard-coded for like cryptographic functions or identity functions. One of the thing also to remember is like each address, even though like the registers of the Ethereum virtual machines are on 256 bits, addresses are going to be encoded on 160 bits. So it's quite easy to do like some type discovery to know what's an address or not, because usually you see like an AND operation on it, and you just like, well, at least like in the actual like tool porosity, I just mark it as an address when I see like it's working on 160 bits. So when you have user-defined functions, you can actually like pass parameters. Like I was saying, to call an actual function in a smart contract under the hood, what it does is it's passing the actual hash of the function. So, and then you would pass like the actual parameters in the environment information block. So the first 4 bytes will be the hash signature, and then you would pass your actual parameters. So here you have an instruction called data load. So offset 4 would be the first parameter, and 24 would be like the second parameter, because you are passing like integers to the function. So they're encoded on 256 bits. And that will be your pseudocode for that actual solidity function. So it's a bit confusing at the beginning, but then you realize it's quite straightforward and very easy. Type discovery, like I was saying with addresses, they are basically like encoded on 160 bits. So nothing complicated here. You're going to have some variation done by the actual compiler for optimization. Sometimes you just see like a big AND with like that giant mask, and sometimes it just like computes it dynamically, like what we see here using the exponential function, which works pretty well. So now with bytecode. So once you compile your actual smart contract, like I was saying, you get some bytecode. And then, you know, like another thing that could have been like optimized, which is not, is you're still going to have the actual preloader of your smart contract inside your bytecode. So whenever it's actually like compiled in the blockchain, you would have like the preloader, which does a bunch of like things that could probably like just like be removed, and then the actual like runtime code of the contract. So the preloader is like pretty classic. It's always like the same thing over and over. It would just basically like take the runtime code and copy it in memory, then to be later to be executed later on. The runtime part is basically where we focus on to do our analysis, and that's where you can do like all the function discovery, parameter discovery, and so regarding the preloader, so the most important instruction is called code copy, which is gonna copies the runtime code in memory, and then it's gonna copy it at the offset 0. That's where the execution is gonna happen. So nothing too complicated here. And then we have our actual like dispatcher. So the actual runtime code is basically a big dispatcher. So for each function you're gonna have the equivalent of a big switched. And for like each function, you're gonna have a 4-byte signature, so 32 bits integer, which is gonna be like compared, and then for each, and once it matches, it's gonna like route you to the actual correct function. So whenever you do like the dispatcher analysis, that's where you kind of like see where your function is or not. So here, in yellow and in pink, we have like two separate functions. So one called double and another one called triple, for the example to explain it. And and as you can see here, so it's gonna push. Also, one of the interesting things is like instead of just having like one push instruction, they have like 32 instructions just for push. They have like push 1 for push 1 byte, push 2 for push 2 bytes. Here it's like push 4 because it's gonna push like 4 bytes. Then you have like push 12 and etc. etc. It's quite an interesting design. To not say weird, but that's the way it is. So here it's quite easy to recognize like all the hash because you just need to look for like all the push for, and right after it you would have an EQ like instruction, which is going to compare like the first two like entries of the stack to see if they're equal or not. Because like in orange, it's going to read the information block where it's going to recover the first 4 bytes of the actual like hash passed to the smart contract. So let's take like the first one, the first function. So if it's equal, it's going to like jump to the address 24. Oh. And once it's passed to 24, you have like that tag, that jump dest instruction saying, okay, that's like the entry point of our current like basic block. What are you doing? You want to talk about blockchain? See, after the crypto kitties, we have the crypto doggies now. Buy now, this address. So after that, like I was saying, the actual like symbols are being passed through like a JSON interface. That's where you would have all your function names and all your parameters. The way the hash is actually computed is pretty straightforward. You're just taking the chaffery of the function name and all the parameters type. And for each of them, it's just going to keep like the first 4 bytes, and that's it. That's all you have your signatures. So here, for instance, for double, that's an example here. That's basically your hash. So every time you're going to call the double in function, that's what you will see. So also one of the interesting things, so let's say in the case of parity, is whenever like something like big happen, like like some wallets are being frozen, we want to look at what happened. So from an incident response point of view, because everything is logged, each call to the functions are being logged as transactions. So you can actually like look back to the actual call stack, or stack call, I forgot who you said, of all the functions being called. And you can also see like each parameters. So if you look at the actual like call stack of it, you would see that the first 4 bytes would correspond to the function, so you would have to refer to the interface that you have to know which function has been called. So from an incident response point of view, it's quite interesting because you can actually replay an attack very easily, which is what happened with the parity thing. Like as soon as that guy was just like arriving on GitHub saying, oh, damn, I think I locked everyone's money. Well, at least everyone could like have a look at the last transactions and see which one looked dodgy. So that's so an hash is being extracted. So I covered it. I'm just giving you like a compared view of if you use like a purely like static analysis. So you see like there's some basic blocks that are basically like orphans. We don't know where they come from because of those like weird stack manipulation in memory. So you're gonna have to emulate the actual like call stack to understand where the call is going to. So if we would translate the actual runtime code, that's what it would look like on a raw view, and then you have like the clean view on the right. So as I was saying, it's basically like a big switch, and it takes like each like function signature, and then it reroutes you to the actual function. And then in some cases, so here, because it's doing some arithmetic operation, it's going to use like the volatile memory. So internally, it would use like the mstore and mload instructions. That's where we see like those memory with the address being used. So that's for the volatile memory. So here, if we would look at the actual execution, so the signature would be passed. Then we would push. So we'd read like the actual like first parameter. And then we'd push like the 2. And here, that basic block is shared by the 2 functions for optimization purposes. And then it would call the multiply instruction. And that's pretty much it. Then it would just exit. Same thing for triple. It would read the first parameter, push like 3, because we multiply by 3, go back to the common basic block, execute it, and then it would leave. So, so few interesting bugs happened last year. So parity really suffered. They got like at least like 2 different bugs that were like pretty major. So one of them, people like stole like 30 million. So like I was saying, you can call like third-party libraries. So in theory, like smart contracts were designed to be very simple. It was supposed to do very simple instructions. That's why now you have like new languages called like simplicity, trying to limit the actual capabilities of the developers. What happened with Ethereum and Solidity is they kind of like try to do like this rich like virtual machine and language, which is like, you know, like could have been a good idea, but that would have required like more work. But whenever you give developers like too much like power on what they can write, you know, they start to like make things that are overcomplicated. Especially with like web developers, you know, like if you do like web development now with all the microservices, you know, with all the containers, people like tend to overcomplicate some stuff. So the same thing is actually currently happening with smart contracts. So here you had a Bytecode library. So here, like that's a simplified view of the actual bug. So the address is hard-coded inside the smart contract. And then you have this instruction called delegate call. So then to call like the, it's kind of weird, you know, like they hard code like all the functions. It's like a mix between like inline assembly and like JavaScript. So that would be like the equivalent of the Ethereum inline assembly. It would call the function, and then so at the back, at the very end, you have this function with no name. So it's like the default fallback function. So one of the main reasons they have fallback functions with smart contracts is because, like I was saying, if you put code in the blockchain, it's immutable. You cannot patch it, right? So you need to think of a way to be like, you know, like also to have like this issue of being like backward compatible for like interoperability purposes. While like here it's like the issue is like, well, you have to be backward compatible and forward compatible. So that's why they have like this generic function that can like forward stuff like later on. Which is kind of weird, you know, it doesn't make any sense, but whatever. So you have this function. If function name is not known, it would like call delegate call. And the interesting part here is when the delegate call happens, is it gives you like full control on the data from the environment block. So if you look up, at least it's passing like the hash of the function. You know it's passing an actual hash of a function. It was like here, like the default function, you know, which in theory would have like if you would do it like properly, would have been supposed to be marked as like internal, you know, like as a private function if you're like a C# developer. So here it was not marked as public or private, so there is no such thing. And they give you like full control on it, which means basically you can put the hash of any function you want. So you can call like any function you want inside the wallet library. So first, it's kind of like too much power for like the user. So that's one of the that was one of the first mistake. So like I was saying, one of the issue is that they have to be like forward and backward compatible, fallback functions. A lot of the issues are like related to it. Even like with the DAO hack that happened, it was due to like one of those like fallback function. So that's the actual fix. So the first thing they did is to define some function as private, so with the internal attribute, and then and then, so the init wallet function now can only be called if it had been, if it's like currently initialized. So what happened is like the attacker, what they did, or the attackers, you know, who knows how many like masterminds were behind it. Basically, like recall the init wallet function a second time, so they could just like reinitialize it, which was like the main problem. So, I mean, it's kind of like stupid, you know. It's like, you know, when Windows 32K didn't have to have like proper like probing like function at the beginning to filter parameters. Well, it's pretty much like the equivalent. There is no like probing of arguments being passed. But the problem is, like, it's not a blue screen of death, you know, at the end. You know, it's like it's actually extracting like money. So that's a pretty good target for attackers, to be honest. And since everybody is like pouring more like money in that garbage, well, more stuff is gonna happen. So that one was pretty funny. That happened in November. So this is like this guy. He was basically like on GitHub who said, "Oh, I accidentally like killed it," you know, with no explanation. Everybody was like, "Oh, what does it mean?" And so that's what I was saying before. Is like the thing is, if for incident response purposes, it's quite interesting because you still have access to the call stack. So instead of having like a crash dump, you know, from like something that happened, well, you still have the call stack of even like transactions that were valid. So he just gave like the link. And you would see that basically it did 2 transactions. So the first one, what it did, it was a separate bug, but it took like ownership of the library, and and the second, I have no idea why they put all those functions. Like literally, they just like do like the weirdest stuff ever. So they had like a function called like kill that would destroy like all the contracts. So once he had ownership of it, well, he was scared someone would take over like that bug, so he decided to kill everything. So that's why like all those like 300 or 400 million like got like frozen. And then people like went into that argument again, like, oh, should we do a fork or not? You know, because that's basically like the only way they could recover money. But because it's decentralized, you know, well, nobody is gonna do a fucking fork, you know, like they don't care. They did it like once, you know, but now like people are done, you know, like they keep talking about fork every month. So never gonna happen. The guy was scared to be arrested. That was pretty funny to read, at least if you had no money on it. Although it's pretty sad. But so what happened? The actual the actual bug. I'm trying to remember it now. So there is no distinction between an application and a library. You know, like on like now on Windows, if you write an executable, it's different from like a DLL, right? There is like that concept of it's not the same thing. You have like dynamic library, and then you have like application. While in the blockchain world, everything is like code. You know, it doesn't matter. You know, they call it library, wallet, whatever, but just like code. So what happened is, so he used like the bug to turn one of the actual issue, like the main library, he turned it into wallet. So he turned the you know, like the library into an application, and because like the actual library is a library, it's not supposed to have any owner, unlike when you give like a wallet to someone. But by design, you know, like the wallet could have been turned into a wallet directly, which is what he did. So he took ownership of the global library that was used by like all the smart contracts, all the wallets managed by Parity. And then he called like the suicide function, which does what the name does, you know, just like killed it all. So like those posts are still probably on GitHub, but I think they're probably like the funniest stuff online after like all the blog posts from shadow brokers. But yeah, so he was like explaining what he tried to do, how confused he was. And then he's like, oh, I believe someone might exploit it. And even you see, like, he closed like the actual like GitHub issue, and then he reopens it. He's like, oh, I just killed everything, you know. So yeah, that was a pretty funny one. So here is like an example of another like smart contract which is vulnerable. So that's the type of bugs we can actually detect with the tool porosity. So here is like a simplified version of the DAO smart contract that got hacked. So usually a lot of the functions you would see are pretty similar, regardless if it's like a token or anything. You would have a balance, you would add money, you would withdraw money. It will always come down to like adding or subtracting a value to like some array in memory. So here, what's interesting and what people didn't think about is, so call value is like another way to call like a third-party library. Is you can recall yourself because you can execute like you can have like the equivalent of a race condition with smart contracts, which is basically what happened with the actual fallback function. So here, the actual error was not handled properly. So you would think like, okay, like there is a throw, it happens, that's it. But the problem is like the balance was only initialized to 0 after at the end. So you know, instead of like, okay, like let's make sure like the balance is like proper or not. So that's where like the race condition was. So they call it like a reentrant vulnerability. So from the porosity point of view, if you do like some disassembly of a smart contract, the way you identify it is quite straightforward. You would look for a call to a third-party library, like what we see here, like we see like a call value to it. And then we would track if there is like any modification to the permanent memory done afterwards. So in that case, we would look specifically at the store instruction. And then we would just track each basic blocks and their relationship with each other. So here, so that's an example. If you would use like porosity, you would provide the bytecode, and then you would provide the interface. Then you would run the tool, so that's like the only two parameters it would require. Then once you would decompile it, so it would like go through the dispatch function, so the runtime code, split all the different functions, and for each function it would analyze each basic blocks and taint each basic block to see if there is like any modification to the permanent memory, the storage memory, done after a call to like a third-party library. So here, that's basically how you would detect it. Then, you know, because it's pretty easy like to disassemble, it's not too complex. The tool would just highlight it. And that's pretty much it, you know. Then you would have your vulnerability being highlighted. So now, so far, there are like few bugs that have been highlighted. So the delegate call was a new type of bug that was discovered with the parity wallet when all the wallet got frozen. So far, there is not too many like classes of bugs around smart contracts that have been known. Most of them, when you read about them, you know they're like pretty straightforward to understand. And now there's like more tools to help developers of smart contract to actually like, well, do a static analysis of their tool, like Mitril or Oyente or Pority. So now it's interesting to see like the actual like security scene around like smart contract being developed. We integrated with Quorum, which is like the Ethereum fork, with like a privacy layer, because now with Ethereum everything is public. So Quorum came up saying, okay, we need like a privacy layer, so not everything is public in the our blockchain. So we integrated with it because the architecture is very similar to Ethereum. And now what gets interesting is basically what to expect in terms of issues like for T0. So some of them actually happen over the past few weeks. It's kind of interesting scene because like every like 2 weeks, like something new is happening. So what happened, like I was saying, blockchain applications, dynamic applications, smart contracts are basically like the same thing, but there are like this new layer of application that people are using more and more. Just like when mobile applications were emerging, it was kind of like, oh, should we spend time looking at it or not? So it's kind of like in that category. Now, there is more like people looking at security around it, and so when I send my slide, no one actually published any vulnerability inside the Ethereum virtual machine, but just happened a week ago. So it didn't provide a code, a remote code execution for the actual EVM, but why not? It's bound to happen at some point. There is a C++ implementation and a Go implementation of Ethereum. So the C++ implementation is definitely going to have bugs. And like I was saying, I think it was Tiz1. So Talos, Cisco Talos found some bug in the EVM itself. So they did not manage to actually trigger a code execution out of it, only just a DOS, a crash. But that's still pretty interesting because it shows that VMs also can have vulnerabilities, which obviously we knew because we have seen it many times with VMware Workstation or ESX or even with Hyper-V. But people in the blockchain world are kind of living in that bubble where they think everything is secure. So it's kind of interesting to see the world crumbling under their feet. And then there is a bunch of web security vulnerabilities that also happen. So with the policy vulnerabilities, it's also highly dependent on JSON libraries. So another vulnerability was found by the same team. Something also interesting, which is supposed to be on the roadmap. So I remember talking with the developers. I asked them when it's going to be on the roadmap. They said they're going to do a test run in January, but I haven't seen it yet. So they were planning to use WebAssembly as a virtual machine instead of the Ethereum virtual machine. So some people are looking at an actual replacement for the EVM. I was a bit like curious of how it would work, but basically each instructions from the Ethereum virtual machine is just being rewritten in what the name? The WAST, like the web assembly language. So it's an interesting way to replace it, but still like highly dependent on the actual like current architecture, like all the like the memory and the registers, or the way all those things are done. But then you potentially, you know, it could also like trigger like vulnerabilities inside like the WebAssembly engine. So smart contracts, so there is some new virtual machines emerging, like ChainVM. IELE is pretty interesting, actually. It's probably like the one I would like focus on like this year if I would have time. The people who are like designing it used to work on the EVM, and they saw like all those limitations with the stack and everything, even with the languages, the fact that you can write smart contracts using a language that you cannot verify in a non-verifiable language is a pretty like strong limitation, especially if you are like aiming at being used by financial institutions. So like Plutos is also a very interesting language to look at. So like Plutos and IELE are going to be part of the Carnado project. So I haven't spent like much time on it, but it seems interesting. Simplicity is just like Solidity, but like a much simpler version of it to avoid like bugs due to like over complexity in smart contract. People are like bringing SGX more and more into it. Microsoft also like even Moxie announced like mobile coins. Microsoft announced like Coco framework. Or is it going to be used so far like in the context of Ethereum or of any like blockchain like VM is still like to be decided. But we already know that with the create enclave function, you can already create your own enclave, so it's supporting like the virtual base enclave and the SGX one. So like interesting like DLLs to look at, the ones like used for it. It's public, it's on MSDN. And then all the things that happened with Spectrum, some people like looked at how to use it against SGX. I didn't spend much time on it, but it sounded quite interesting. But again, in the context of like a blockchain VM, it does not really matter much if you use SGX or not. Yeah, so 2 blog posts that are interesting to look at, like kind of like my vision for like this year with what's going to happen with smart contracts. The Talos blog post was cool. And if you have any questions, you can just like send me a message on Twitter, or you can just look at the white paper on GitHub. Toda.